Hello everyone. Today we're going to solve the 2011 USAJMO problem number 1. So find with proof all positive integers n for which 2 to the power of n plus 12n plus 2011n is a perfect square. A simple one sentence problem. I mean simple that there's only one sentence, but the problem itself is not that easy. Okay, so we need to find all positive integers n. So n must be bigger or equal than 1. Cannot count n equals 0. But even if n was 0, we would have 2 to the 0 plus 12 to the 0 plus 2011 to the 0. That would be equal to 3. And that's not a perfect square. So let's first try some values of n to get. But actually, the only value we can try is n equals to 1. So that will be the sum of 2 plus 12 plus 2011. That will be 32 plus 2. That will be 2025. And that is equal to 45 squared, I think. Like, you should know that. That's important. Equal to 45 squared. So n equals 1 works. So we can quickly see that we cannot find any value further than n equals 2 because 2011 square is way too big for us to calculate because we don't have a calculator. So the only way to solve this is to use a modular argument. So we are going to we're going to use modular arithmetic to reduce this sum into smaller sums that we can use to solve this problem. So what if we take modulo 2? But actually modulo 2 would be too small because we would have to cancel this and cancel this. So if 2n plus 12n plus 2011n, that would be simply equal to 1 modulo 2. And that's not very useful for our purposes because that gives 0, 0, and that gives 1. That's not very useful. So that's x. So what if we can use modular 12 so that we can cancel this term? So let's see. 2 to the n plus 12 to the n plus 2011 to the n. What is it equal when it's modular? So clearly that is 0. And this we don't know. And this we can do 2011 modular 12. So that will be 81, that will be 6, 72, and that will be 91, I think. 6, 72. That will yield 7, I think. Wait, no. No, I did that. I did an error. That's 7. So it's 84. So that will be 7. So yeah. So we have 167 and the remainder is 7. So we would have 7 to the power of n. So when we take mod of 12, that'll be equal to 2 power of n plus 7 power of n. So now we have reduced our equation to this one. So how can we proceed? We 2 power of n plus 7 power of n. And we need to prove that this is a whether this is a perfect square, there exists a perfect square, or whether it's impossible to have any perfect square. So let's see, because we have smaller values of n, it's way easier to work with these. So let's suppose that we already know that n equals 1 works. So let's try n equals 2. N equals 2, that will be 2 squared plus 7 squared is equal to, let's say, 4 plus 49, that's equal to 53. So what is 53 mod 12? So that is equal to 53 minus 48. So that will be 5. Mod 12. So what if n equals 3? Let's try. That will be 2 to the 3 plus 7 to the 3. That's equal to 8 plus 343. That's equal to what? That's equal to 351. And mod 12, I'll do division. That will be 24, that will be 11. We have a remainder of 3. Okay. Mod what? Now we're getting bigger numbers. How about we simplify it 2n plus 7n mod 12 as 2n plus minus 5 of n. We would have better results because 7 to the n mod 12, that will be similar to minus 5 because we're subtracting 12. So let's see, and when n is equal to 4, so that will be 2 to the 4 plus minus 5 to the 4. That's the same as 5 to the 4. So that will be 16 plus 625. So we had 6 to 641 was this mod 12. That's equal to okay, that's 41, 12, that's 36. We have a remainder of 5. That's pretty odd because we had a 5 here and we have a 3 here, and again we have a 5 here. So probably we're seeing a pattern. But let's try the n equals 5. What if n equals 5? If it's 3, so we got a pattern. Or if it's something else, we haven't got it yet. So let's try n equals 5. So that will be 2 to the 5 plus 5 to the 5. That's equal to 32 plus 3,125. Plus 32, that will be 7, 5, 3 ones, 5, 7. What is mod 12 as congruent to that will be 24, 75, 6, 72, 37, yeah, 3. So yeah, we have minus 36. But did I make a mistake? 1. Oh, I made a big mistake here, sorry. That's not 5 to the 5, it's minus 5 to the 5. So we're having minus 5 to the 5 here. That's not correct. That'll be minus, and that's not good. Subtraction, that'll be 9. We're having minus 3097 module 12. So that'll be, let's find the biggest value that is bigger. So 3097 divided by 12, that is 2469. 69, okay. 5, 60, 93. We have 12 times 7. So it's 90, 84. So having a rest of 9. So if we have a rest of minus 9, so we're having a rest of minus 9 mod 12. So that'll be congruent to 3 mod 12. So again, as I thought, here we have a 5, and then we have a 3, then we have a 5, and then we have a 3. I'll erase my calculations. So clearly there's a pattern that every value, when n is even, when n is congruent to 0 mod 2, and any value 2n plus 7n is congruent to 5 mod 12. And when n is congruent to 1 mod 12, mod 2, then 2 to the n plus 7 to the n is congruent to 3 mod 12, as we calculated. So we know that only 5 and 3 are possible values of mod 12. But we need to think of the properties of of, of square numbers when we're dealing with this. So what are properties of square numbers? Well, we can say like m squared. What is m squared? Mod 12. What are the possibilities? So clearly 0 is possibility, 1 is possibility, 4, 9. So 16 mod 12 is 4. 25 mod 12. 25 mod 12 is what? That will be equal to 1. 36 mod 12 is 0. 49 mod 12 is 1. So 64 mod 12 is 4. 81 mod 12 is 9. And 100 mod 12 is equal to 4. So clearly we're seeing a pattern here. We're having 0, 1, 4, 9, 4, 4, 1, 0, 1, 4, 9. So repeating 0, 1, 4, and 9. So these are the properties of, these are the only possible remainders of the square numbers. So the only possible remainders are 0, 1, 4, 9. But here we're having remainders of 5 and 3. That's not even correct from the point of view of square numbers. So clearly we're having a contradiction because the only possible remainders of square numbers mod 12 are 0, 1, 4, and 9, whereas in this expression we have remainders of 3 and 5. So we're having a contradiction here. So from all of this point, we're only trying to get the possible values or replacements of, no, not replacement, the possible remainders when taking mod 12. So that shouldn't be written in your official solution. So basically, so we're done with the problem because we have a contradiction here. So the only possible answer is when n is equal to 1. So find with the proof of positive integers n for which 2n minus plus 12n plus 2011n is a perfect square. So we can safely assume that we're using a proof by contradiction. So this problem is pretty a number theory problem that tests a lot of your uh, knowledge about modular arithmetic and all sorts of stuff that are pretty important for this problem. So I hope this recording helped you, and see you soon.